what we did in the previous slide is if we evaluated the amputated Green's function to be of this form. Now, amputation was needed only to identify what we mean by 1pi. It's basically Green's function, the actual Green's function with the external legs removed. So once we understand what 1pi or 1pi, non-1pi blobs mean, we don't need to consider amputated diagrams in amputated diagrams anymore. So let's write this expression for G3, G tilde 3, P1, P2, P3. This we have shown to have structured like this. Where this 1pi is a 1pi 3 vertex. Okay, and they have okay, so the momentum, this is P1, this is P2, and this is P3. Now I will now try to convince you or try to help you see a pattern in order to arrive at this form. You see what we have basically found is that there is a tree level diagram in G tilde 3. There is a tree level diagram, which is this primitive vertex, and then when we add up all corrections, quantum corrections, but we have a connected diagram. We are looking at a connected diagram. When we add up all the corrections, then there are basically two broad topological categories in which the corrections can appear. One is that it can replace the vertex with some resolved, it can replace the vertex with some resolved diagram with various loops. You know, it can be quite complicated and all sorts of things. All the diagram, all this corrections added together, they are basically as if blowing up that that single point into a fuzzy interacting region. That is one type of diagrams. And the other type of diagrams are where the legs are getting corrected. Okay, so if you that means if you add all these for each diagram in this first category, all the diagrams in the second category will appear. So this is like a multiplication. Okay, it's like you multiply this topological class with this other topological class, so that you get there are infinite number of diagrams of this sort. There are infinite number of diagrams of this sort: single leg, double leg, and three leg corrections. Okay, so each leg is like so there's a structure of this multiplied by this, which is leg. This is vertex, this is leg, and this is also leg, and this is the third leg. So it is a structure like that, where in each square bracket we have infinite number of diagrams, right? So this is like the diagrams of the first leg, like this kind of diagram. This is the second the corrections in the second leg, and so on. So this like it has a factorized form, and therefore we are able to write that enables us to write this form. Like for each leg, we just use the exact propagator with all the corrections, and the vertex is replaced by a 3.1 pi. So the idea is clear. For any higher point functions, for any higher point Green's function, what we should do is to look at the tree diagrams and then understand what are the topological categories, and then try to find, and then try to classify them in this type of forms. So let us do that for G tilde 4, n equal to 4. Now G tilde 4, what are the tree diagrams? So in this case, there are the tree diagrams are, one is this, then there are actually 4 categories. There are 4 types of tree diagrams. Now, this is certainly not present in the theory as a primitive vertex, but the topology, I mean, but the corrections to that topology exist in phi cube theory. For example, you can have from here, you will have a correction like this. This is present in the theory. This is constructed out of 3 vertices. Then you can make arbitrary complicated loop. For example, this one, or this one. These are all present in the phi cube theory. But as far as the topological, categorization is involved, it is basically related to this tree diagram, though the tree diagram by itself is not present. So that gives you so from here you will get, of course, all these diagrams, just exactly like in the n equal to 3 case. All these diagrams added together will give you a 4.1 pi, and then there are leg corrections, and therefore you will end up getting a diagram like this. This is a 4.1 pi. And this is a new interaction, because you see, you probably now can guess from here, all these topological categories will lead to a structure where only 3.1 pi will be involved. I'm not going to repeat the same arguments here, but it is quite clear that from here you will get a diagram like this. From here, so these are the 4 categories, that 4 types of diagrams. And of course, in all these 3 diagrams, you have 3 vertices appearing. These 3 vertices, this 3.1 pi vertex was introduced while calculating G tilde 3. So it is the less than n equal to 4. right? I mean, now you can proceed to do the same calculations, same type of classifications for any higher value of n, capital N, and the prescription is quite straightforward. You will have to you will have to look at the tree diagrams and replace and blow up everything, like all these propagators to the exact propagators and the vertices to 1 pi vertices. Now, before proceeding further, let me write down the position space expressions as well. I haven't written it there, so let me do it with the four vertex. I would have ideally done with the 3 vertex because it's a simpler. There are 3 legs, but let me do it for the case of 4 vertex anyway. So in position space, you will be writing G4 connected x1, x2, x3, and x4. Now recall, we actually started out with position space Green's function and then did Fourier transform to go to momentum space Green's function. And one thing we noticed that in position space you will have 4 external points, or maybe yeah, in position, maybe let's take this diagram, 4 external points. But when you go to momentum space, then each external point is replaced by the incoming external momentum, right? That was the change. Otherwise, the topology of the graph remains exactly the same. There is no difference in the graph, except that in the position space, all the points, like external points, are crosses. And those are the external points, and the internal vertices are space-time points which are integrated over. In the corresponding momentum space expression, these crosses are replaced by incoming arrow, because those are momenta. And the internal points will not have any x space-time point associated with it, but all the individual lines will have momentum specification, and there will be momentum integrals. So the loop will be integrated over. So basically what it means that the topology of the diagram remains exactly the same in position space representation and momentum space representation. It is the style of how different parts of the diagram are labeled that changes. So, and we know how it changes. So in this case, we have an expression, we have a diagram, which is x from x1, you get the connected Green's function. This connected Green's function is in position space, and then you have 1 pi. This is x1, x2, x3, and x4. And now, so therefore, this 1 pi is a position space in position space representation. This is a 4.1 pi, but in position space representation. In momentum space representation, 4.1 pi will have 4 arguments, which are the momenta, external momenta, p1, p2, p3, p4. But in position space representation, there will be 4 arguments, which are 4 space-time points, say u1, u2, u3, u1, u2, u3, u4. So therefore, the total, the exact moment, the exact propagator, which in momentum space language had a momentum p, is now has now in position space representation will have. So in momentum space, it has p1 and p2 with overall delta function. It becomes p. In position space, it will have 2 two endpoints. The propagator will have two endpoints, x1 and u1, and this u1 is the external point of this 1pi, external point of the 1pi, and since it's an internal point of the entire diagram, this u must be integrated over. Therefore, what I have is the following: minus I over h bar integral du1 du2 du3 du4. Then the four propagators, which are the connected two-point functions, x1 to u1, then g2 connected x2 to u2, then g2 connected x3 to u3, then g2 connected x4 to u4, and then the this 4-point vertex in position space. 4-point vertex in position space is written as minus I over h bar times gamma 4. That's the definition of gamma 4. So this is as a vertex gamma 4. Now the question is, why is this overall minus I over h bar factor? You recall that in the okay, so there are in the position space, when you write Green's Feynman rules for Green's function in position space, there for each vertex you had a factor of I times g, so factor of I times g times integral over the position of the vertex, right? Now what is this I times g? If you remember, g was actually, so g was actually minus lambda 3. When you write the potential, the couplings for phi to the power n coupling in the Lagrangian, which has a coefficient lambda n by factorial n, so for cubic vertex it will be lambda 3, so minus I lambda 3, because we said that we do not want to deal with this minus sign all the time, so we are changing the sign of the coupling, which is why we originally had this notation for the coupling as lambda n, lambda 3, lambda 4, and so on. But for cubic vertex, we introduce a new notation g just to observe this minus sign. That is what is happening now. And those rules were given in h bar equal to 1 unit. So if you recover h bar, that will be minus I by h bar lambda 3, right? You can also convince, this is the shortest way I explained, you can also convince yourself by going into the action. Action has the path integral phase is e to the power I by h bar times action. Action has negative potential, so that gives you minus I by h bar times potential, and the potential has the coupling lambda. Okay, so then minus, therefore in the Feynman rule for the vertex factor, you have minus I by h bar times the coupling times the integral over the location of the vertex. So you can view it in the exactly the same way. It is minus I by h bar times the coupling. This coupling comes, this coupling is outside the integral, so you may also view it as minus I over h bar integral dx lambda 3. But doesn't matter because lambda 3 is a constant. But if you view it this way, that is the view here. Here the vertex is not a single point, but it has been resolved because it has become a 4.1 pi. the vertex has blown up because it has taken all the corrections, all the loop corrections. So it is not a single point anymore. Topologically, it is the vertex. It is in the same topological category of a primitive vertex, but is actually a blob. It has blown up in a finite size, in the sense that there are many loop diagrams inside. Okay, and so on. So therefore, it is a 4-point vertex, and therefore, instead of having a single integral of a vertex, you have 4 integrals here. And then this vertex factor lambda3 is replaced by the function of those 4 points, that is gamma 4. So this is like the vertex factor. What we had, a vertex factor, a coupling of a in the original action. What we had, the coupling of the original in the original action. Analog of that here is this lambda 4. So basically, what we are heading towards is we are going to find an effective action where this gamma 4 will appear as a coupling, exactly like lambda 3 appeared in the original action, field theory action, that we started out with, the classical action. The classical action, in the classical action, what was a point interaction? That point interaction has a coupling lambda 3 or lambda n for an arbitrary n. In the full quantum effective action, you have that point interaction has blown up into an effective interaction like this, where gamma 4 plays the role of lambda 3. Sorry, not lambda 3, but lambda 4. It's corresponding to. Okay, so that is another thing. So it will be gamma 3, ideally speaking. Whatever I just said here, if I'm drawing analogy between this and the thing, I should be comparing an expression, position space expression here. But I think it is easy to understand what I'm saying. Now, in the original action, the classical action, though I have a phi cube term only, there are no phi 4, phi to the power 5, 6 or higher order terms, but it will generate a quantum effective action, will have all powers, which is why in the phi cube theory, we have in the quantum effective action a coupling of gamma 4. This is because of this diagrammatics you are already convinced. Now, this is what I'm saying all is like is like advertisement of what we are going to see in detail at the end, just to motivate this minus I by h bar factor. I mean, it is just a definition. You don't question this, why there is a minus I by h bar factor, but to explain why it is there, I'm giving all this reasoning. But we will see this structure, coming out in detail as we go on. So that is how so that is the vertex factor, the 1pi vertex factor would mean eventually. Now let me generalize this entire thing to arbitrary n. We now see the pattern. We are calculating n-point connected Green's function with external point x1 to xn, and it is given by the diagram is a connected diagram with x1, x2, x3, and so on. And these will have a structure where the n-point 1pi appears for the first time. So this is gamma n plus all tree diagrams involving gamma small n's for n less than less than capital N. So all the other diagrams, just like in G4, we had three other diagrams with cubic 1 pi vertex. Here also you will have all the tree level diagrams. You have to see what are the tree level diagrams you can draw using all possible values of n. Now the thing is that gamma 4, though there is no primitive vertex in the theory, which is 4 point, right? This is not present, but gamma 4 is present. That's what I'm trying to say. So when you draw the tree diagrams, you consider all the lower point vertices, 1 pi vertices, and try to draw the tree diagrams without worrying whether that primitive vertex exists or not. 4 point primitive vertex does not exist, but 4 point primitive vertex will give rise to higher points, point gamma n, GNs. Okay, so now and then the general expression for this term will be minus I over h bar integral du1 to dun g2 connected x1 u1 to g2 connected xn un, and then gamma n u1 to un. That will be the expression. Now let me introduce effective action. Given all this definition of gamma n's 1 pi vertices, let me now introduce effective action. Here you first define classical field. Phi classical x is by definition the vacuum expectation value of phi hat of x in presence of current. So this notation I'm going to use for vacuum expectation value. So there is a field phi hat of x, and the vacuum in the vacuum, if you introduce a current, if you introduce a source J, then what is the vacuum expectation value of the field? That is what basically it means, the notation means, and that is given by we have already defined the vacuum expectation value in absence of J, and there when we define vacuum expectation value in absence of J, what we did is that we took the derivative of the connected Z with respect to Ij and set J equal to 0. Now we don't do that. We keep the J arbitrary. It is not 0. Okay, that's a definition. So phi classical is a configuration that is produced by all the J's. If you remember the diagrammatically, you know this derivative del ijx is acting on all these diagrams. Okay, so it doesn't matter whether I consider tadpole or not. It is just a demonstration. This plus this and so on, and then this. All these higher point J's are there, Now, when we calculated the vacuum expectation value of a field or a time ordered product of multiple fields, we had these derivatives. Those derivatives were acting on these J factors. These are the J's which are integrated over. Now, this J, the derivative is going to act on these dots and bring it down to a fixed point. The integral will be brought down to a fixed point. If you have only one derivative, then one dot will be removed, will become an external point. This dot will become an external point. One of them, right? There are symmetries, etc., that you have to take into account. But after that, what you will get is this expression where these dots, the dots that are remaining, are still integrated over. Those are the value, those are the J's. In the usual vacuum expression value, we said J equal to 0. So all these terms vanish and only this line remains. And that is the vacuum expression value, non-zero vacuum expression value in presence of a tadpole. If we remove the tadpole, then it is not there and the expectation value is 0. But in this phi classical, what we are doing is that we are keeping J non-zero. That means we have all these infinite number of terms with J to the power 0, J to the power 1, then J square, J cube, and all higher order, higher powers of J will appear. So that what it means is that given a value of J, given a J function, a source function, you can calculate the corresponding. This is the expression that tells you the corresponding classical field, phi classical. That is the meaning of this definition. Now then define effective action. Effective action gamma of phi CL is a functional of this classical field, which is by definition is a Legendre transformation of Zj with respect to J. So this is given by I H bar Zj minus H bar J phi CL. That is the definition. Consider this to be a definition. So Legendre transformation, you take J and phi to be the pair of variables under which you perform Legendre transformation of Zj, and what you get is a functional of phi classical, and that's the effective action. That's the definition. And what it means is that if you calculate, this means that if you calculate the derivative of gamma with respect to phi CLX, then that is given by, so this is the derivative acting on the first term will be 0, and the derivative acting on here will be non-zero, and that will be minus H bar times Jx. So this is minus H bar times Jx. So this is a definition of phi classical, and given that phi classical, you do a Legendre transformation with respect to Zj. Zj is given by this object, and then whatever the action you get has the property that the first order derivative with respect to phi classical is minus H bar times Zj, H bar times Jx. Okay.